Welcome to the Global Virtual Lecture Hall. Welcome to the last lecture in this series on artificial intelligence. Today, I think we have a very exciting program, Future Trends 2 and final comments. Let me just, as usual, make the first round of welcome. So Beijing and Jeddah will not be joining today. They're both on vacation. You know, I'm really jealous here. Can we switch to Warsaw quickly? Warsaw, Witold?
Hello, hello.
Good morning.
Good morning.
Good to see you again.
Yeah, everything okay. We have the winter still.
Okay.
Winter.
Very good. So talk to you later. Okay, can you switch to Łódź now, quickly, to Łódź? Good morning. Oh, we didn't hear anything. Is the connection working? Could you talk again, please? We don't have any sound. I think we have to solve the problem with the sound. We don't hear the sound. Okay, maybe Maria and Hanspeter, you can see what you can do about the sound. Okay, can we switch to Munich now?
Good morning, Rolf. Here's
Good
Munich.
morning. Hi, so we will have a presentation today by Munich, I understand, by Angelika Böck, and maybe Ernst Höppel would also like to make a few comments. Okay, well, good morning, everybody. So that seems to be working, and can we now switch to Zurich?
Good morning.
Okay, good morning, Simon.
Nice
How are you?
Very well. I managed to wake up
Okay.
this morning. So you can see.
So the connection seems to be working as well. Okay. Okay, can we now switch back to Tokyo? So the connections mostly seem to be working today. Today's program is we have the Future Trends presentations. I think I'm very, very excited. I think we have really the very best leading people in the field today. And then after these presentations, we will have the presentation of the live logo by Angelika Böck from Munich. And finally, we will try to come up with some summary comments. I would now like to pass the floor to Professor Yasuo Kuniyoshi, who is going to be the moderator today. Please, Yasuo.
Okay, hello. Welcome to Future Trends 2. As I said last time, this Future Trends session is organized by me and Britta Glatzeder, who is the project manager. And the purpose is to present you the frontier and future of intelligent systems and robotics, and bring you an opportunity to hear from world-leading researchers from various sites which is attending this lecture. Okay. So today's Future Trends 2, we have the guest speakers, all three from Japan. The first speaker is Professor Shigeo Hirose in Tokyo Institute of Technology. He's talking about biologically inspired robots. Then we have Professor Yoshihiko Nakamura from this University of Tokyo, and he's talking about modeling human body and mind by dynamics and the future of the new approach to intelligence. Then we have a break, and then Professor Minoru Asada from Osaka University will talk about cognitive developmental robotics. And then we have concluding session in which we have discussions with special guests, Luke Steels, and if any other shows up. And also we have a live logo presentations. So let's move on to the first lecture, titled Biologically Inspired Robots. Professor Shigeo Hirose is at the Department of Mechanical and Aerospace Engineering of Tokyo Institute of Technology. And his field is creative design of robotic systems. And he is a world-famous robot mechanism creator. And he's a former project leader of Super Mechano Systems project. So, please, Professor Hirose, comes up. Okay, please start.
Hi, good evening and good morning, everybody. Today I'll speak about biologically inspired robots. As the time is limited, I would mainly talk about my main interest. It's about snake. Next. Today I'll speak about the mechanism of the motion of the real snake, and also speak about snake-like robots, and talk a little bit about the way of thinking to get the inspiration from the biological system. Well, it's an old story. I entered the Tokyo Institute of Technology as a graduate student, and I interested in motion of the snake. Well, the snake has a slender, very simple body, but once it moves, it can move around in a narrow space, like this, like this, or it can crawl around object like this. And if the snake moves from branch to branch, a part of the body acts as a arm or leg and gripper. Okay, so it's a very interesting animal. We don't have such interesting machine. So I decided to study about the snake. And this is a cartoon I made in the presentation of my doctor thesis. And I want to make active wire, or if we meteorize, we'll make active gastroscope like this. Or it may be useful to inspect very uneven terrain. And even if we use a hydraulic system, actuators, hydraulic power of the hose, maybe we'll make this kind of active hose. And we'll also make amphibious vehicle like this. So, as we have a dream, we decided to study about the snake. But until that time, very little was known about the mechanism of the snake. 最初の this is a experiment I did with a typical Japanese snake. It's not poisonous. And we put artificial lawn, and we make an inclination, and I take a motion from the above. And we didn't know why the snake can move so smoothly without leg. And the next, please. And if the snake is on a very slippery ground, it changes mode of locomotion. If the surface is very slippery, then the snake try to go forward. So the mode is very different. So even though the snake, the intelligence of the snake is very limited, still it shows a very adaptive motion. The next slide. And the snake motion is introduced in Discovery Channel. So I cited this, but so snake had a leg at first, but it decided to adapt to the very narrow space among the rocks to avoid the attack of another animals, and so it becomes very slender. So there's some remains of the legs, and this is one of the motion, but it's not observed typically in the snake observed in Japan. And most okay, please, no more speech, please. This is a side winding. A part of the body is lifted. And this is a swimming motion of the snake. Okay. Anyhow, it adapts to the environment. And as you see, if the snake moves, the curvature is very smooth. And my first interest was this curvature, how we can express. If the body is like this, the curvature, the change of the muscle have to be very rapid. Change should be done on these points, P points. Okay? So it's very strange. It's not natural. And if the body is circular, like this, okay, then curvature is same from OPO. It's the same. And from this side, it's the same. So it's still not so natural. So we can anticipate that the snake body might be sinusoidal. Sinusoidal curve is a very smooth curve. But the smoothness of the sinusoidal curve is true if it is taken to the x-axis. So if we make a derivative of the x-axis, if we continue to derivative, then it's always a continuous function. So that's why it's very continuous. But if we try to get a curvature along the body, it's not so sinusoidal. It's a rather strange curve. So there might be we should use some different curve. And the first curve I thought was a crossoid spiral. Crossoid spiral is a spiral where the curvature changes linearly. So it becomes a spiral. Okay? And it is expressed by the Fresnel integral. And if we connect the crossoid spiral, the shape is like this. And curvature along the body changes linearly. As it's a smooth curve, so crossoid spiral is also used to design the highway. If the curve of the highway is circular, then the driver have to change the steering wheel instantaneously and fix. And at the end of the curve, it returns. So the motion is very strange. But in the case of the crossoid spiral, the driver rotates the steering wheel continuously and return continuously and fix. So it is very smooth. That's why crossoid spiral is used. But still, there are some not continuous part. Therefore, I introduced a special curve where the curvature changes sinusoidally along the s-axis, along the body. Okay. Then the curve should be very continuous, and snakes bent its body sinusoidally. So I thought it's very natural, and I measured. These are the mathematical expression of the curve. We have to use a Bessel function. Anyway, I compared with a real snake, and we magnify the snake motion of any posture and compared with a mathematical expression. And I found it's very code very well. So I found I was very happy. So I know how the snake moves. And afterward, I found that this curve is observed even the waving motion of flagella. So it might be very natural. But it was a long, old story, and I forgot about this problem. But few years ago, I got a letter from emeritus professor of University of California, Berkeley. He said that I wrote a book about this, and the curve is also very similar to the curve of the river. He wrote this book. And he said that this undulating curve is also what I named the serpenoid curve. Because the physical change which generates a curvature changes sinusoidally, then the curve should be like this. And they call it sign-generated curve. And this is an accident, a railway accident, and the stress is introduced in the iron bar. Then this curvature is a sign-generated curve. And this curve is similar to the snake. So it's very interesting. Anyway, what I named the serpenoid curve and what they call the sign-generated curve, anyway, it is found. It's very fundamental in the natural world. And we also studied about the snake mechanism. Some of the book says that the snake uses a scale. This is a kind of a textbook of the snake. And it explains that the snake uses a scale. But it's not true. The snake uses, the surface of the snake is very smooth, backward and backward. And the important point is that there's an edge on the side of the body. So snake uses the edge to go forward. So it's just like ice skating. Okay. So this motion and the snake motion correspond very similarly. Okay. And so, but when I studied about the mechanism, Sir Arthur Gray of England tried to explain about the mechanism by this simple mechanism, a simple structure. There's a spring corresponding to the muscle construction, and then it moves forward. But the important point is that the snake is a multi-joints, but this mechanism is single. So the mechanical is a little different. So I introduced a special equation for the snake motion. These are equations. Anyway, we could derive that the muscle contraction is changes like this, and the resultant force to the ground is like this, cups-like shape. So I wanted to prove this effect by the experiment, and I put the sensors to detect the normal force, and also sensors for electromyography to measure the muscular force. And this is a example of the normal force. It shows that Hasp-like force is really produced. So my assumption was proved. And well, there's a much more interesting phenomena, but as the time limited, I'll skip. Next MOOC, please. Anyhow, in 1972, I made a first snake-like robot. It could move. It has a wheel, but the wheel is passive, and only the shifting the undulating motion from the top to the rear produces a smooth gliding motion. Yeah. And this one is another model. The next one, please. So basically the same motion, but I made it 5 or 6 years ago. So this time we could mount the controlling computers and batteries. So there's no umbilical cord. And the important point of this motion is that this is a motion. And the important point is that it could go forward and backward. If the snake, it uses a scale, it can go backward. But I could demonstrate and go forward and backward motion can be generated at the same time. And I mounted the skate bridge. I made ice skating. Anyway, okay. It's about the sensing problem, but let's skip it. We don't have time. Okay. And this one is the third model. Let's skip it. じゃあ、3つ先のかな。So, this is the latest model of the snake robot. Former model makes only two-dimensional undulating motion, but I added a three-dimensional motion and it's covered with a large-scale wheel, so it could move around anyway and also rotate sideways. And so it shows very versatile mobilities, but let's skip it. Okay, this is the mechanism. And this one is about amphibious vehicle. A snake produce a propulsive motion, only the bending motion. So there's no rotating element. Therefore, it might be very easy to make watertight. And that's why I'm interested in swimming snake. But in nature, there's a very interesting animal, which composed of very small spirochete, very small animal, and the body doesn't swim, but instead it makes it makes rotating motion, just like coil spring. Okay, and important thing is that there's no body. Only the coil spring shaped animal produces propulsive motion. And I was interested in this motion, and I made the next unit. I made a unit and tried to make same motion by the robot. This is a single unit. If you bend and twist this way, it can rotate. So by using this motion, we can make swimming, just like spiral. So it's a watertight snake-like robot, and it has a fin along the body. And all the segments try to bend, and that bend is shifted with to the rear direction, and so it rotates, and rotation is supported by the fin. So therefore, the total body goes forward. And it is never used in an artificial machine, but it might be very effective. For in the case of the undulation, only a part of the body contribute to the propulsion. But in this case, all the body can generate propulsive motion. And so I'm going to use this kind of robot feature. And these are the mechanism, and these are some tricks to make the joint. Okay, let's skip. And the final remark is about our snake robot for inspection for after the earthquake. We had a very big earthquake, and to inspect inside the debris, we need a very slender machine. So we decided to make the movie, please. Slender snake-like robot. But if you try to make a practical robot, if the actuator's number is it's not so practical. So we try to limit the number of actuators. It has only 3 actuators. One drive all 3 crawlers, and another 2 drive the joint simultaneously, synchronous bending. So the motion is still limited, but still it shows a very good performance. And now we are contracting with a company, and the company is interested to use this machine to inspect under the ground of the building. And so this year, maybe they are commercialized. So I studied the snake 30 years ago, and I continue that research, and now it's going to be commercialized. So final remark about the attitude to the biological system. As you see, there's a lots of very interesting phenomena in the biological system. But the important point is that we should get the essence of the information, not try to imitate as it is. For the boundary condition is very different. So we always very pay attention to the nature, but we shouldn't be biased by the nature. That's a very important point. And for this regard, I remember the word of the Miyamoto Musashi. He's a very famous samurai swordman. He foughted many times and never lose a game. There's an anecdote about him. He was going to go a duel, and he passed by the shrine. But normally, the people of this age was very superstitious. They pray, but he didn't do that. And of course, he won a game. Afterward, he was asked why you didn't pray. And he said, we should respect the God, but not rely on it. And it is a very good word, and I like this word. So our attitude to nature is the same. So that's what I want to say. Thank you very much for this.
Thank you very much, Professor Hirose. So I can take a few questions. Any side have questions? Please speak up. And anybody here in Tokyo have questions? We have maybe one. Okay.
Professor, have you think about using artificial muscle to your snakes? I mean, because I know that like at MIT there are some teams that produce artificial muscles, and potentially I think it could be, I don't know, maybe good point to think. I don't know.
Yeah. So when we design the robot like this with multiple degrees of freedom, actuator is one of the essential points, and good actuator is always favorable. But when I made a very tiny active endoscope, I try to use a shape memory alloy. But the problem is that it's not energy efficiency is very low, response time is very limited. So if it's a very tiny machine, it's okay. But in the case of the big machine, of course, I know there's several people studying about a new type of actuators. But until now, the performance is still very limited. So the only solution is electrical actuators. And I'm just now developing a new AC motor with a special reduction gear system. And maybe that's only way, at least as far as I know, most promising. But of course, if there's a good actuator, I welcome.
Thank you. Any other question? Maybe I can take another question if anybody has insights, no questions. All right. I think, yes, we have. Luke, please.
So the movement is very much a function of the structure of the body and less a consequence of, let's say, complex control. Is that right? I'm asking the question because Rolf, of course, has been promoting the idea of embodiment. And so in the example of the snake, this seems to be a very nice example of this kind of philosophy that, the interaction with the world and the physics of the body is the key here to move.
Okay, I as the time was limited, I skipped the problem of the tactile sensors. I attached the tactile sensor along the body, and その迷路に入ってるのを見せれますか? I put the snake robot in the labyrinth, and at that time it's rather simple way of algorithm, but it was very effective to go inside the narrow path. And in that case, the sensing and actuation is very important. But of course, it's a very limited motion, and if we go, for example, the debris to look for people, maybe we need a much more sophisticated controllers. So it's very interesting topic.
Yeah, but probably I think the reason why the shape was so important is probably if you adopt a different shape, maybe it cannot do locomotion very well. Is that the case? If you change the shape,
you mean
it doesn't work well?
Of course, we have a specific, most good shape to produce a maximum propulsive force. But of course, the shape should be changed according to the ground condition. So it has to be adaptive and also very effective.
Okay. Thank you very much. I think Hirose Sensei's lecture pointed out, gave us a very nice essential lesson about biological inspired approach. Thank you very much. And we move on to the next talk. Let me introduce Let me introduce Professor Yoshihiko Nakamura. Actually, he's currently a department head of our Department of Mechanical Informatics of the University of Tokyo. And his field is in control and mechanics, especially probably in non-hologramic and redundant systems, and also motion science. And he's also into medical robots, and probably most related to today's topic, dynamics models of intelligence. So, Professor Nakamura, please.
Well, thank you very much for the kind introduction. First of all, I would like to congratulate the Professor Rolf Pfeifer and Professor Kunz for making this really important project from our department, and especially the inclusion of the many advanced topics in this lecture is really an honor for ourselves. Well, I'd like to take some time introducing some of our recent work. And we have worked on the really long titled project, but we call it the Robot Brain Project. And we conducted this project for 5 years from 1998. Yes, that's right. That's right. And well, this project is focusing on the role of dynamics and connecting the human and the humanoid in a sense, and developing the machine intelligence, focusing on the dynamics between the body and the environment and information processing is the main challenge we try to make. And the issue is very simple. I think the connection of symbols or signs and motion. This is the real challenge of machine intelligence. And of course, the motions is continuous and dynamics, and of course, dynamical stuff. And symbols are, in some cases, the statics and discrete. Combining the discrete stuff and also continuous stuff is really a challenge. Well, the very classical AI has just focused on the static symbols. And of course, the more recently, the embodiment between the symbols and the body, connecting symbols and the body is the main focus of recent activities of AI and many other fields. And I like the idea. And also, of course, the people include the world as a part of the body. And we believe that connecting these three is very important. But somehow the discrete things and continuous things are included. And the question is how we can connect them. Of course, the brain and the body must be tightly coupled and connected in a smooth way. The key idea is how to design the dynamics connecting these two things. Of course, the body and the world must be connected in a sense. The traditional hard-bodied robot is not really a good machines in this sense. So we have to improve the mechanism of the body of robot. We are focusing on the body of humanoid, by the way. And the main activities and research outcome of our project can be listed in this way. Well, and we have 4 things, but I'd like to introduce some of them. First of all, the generation of transition motion patterns by dynamics. I think this subject was already explained by Professor Masafumi Okada as a part of this lecture. So I'd like to just briefly remind you about this project. Maybe movie number 2, please. Okay, the humanoid robot. Well, sorry. Okay, so this is a humanoid robot, and humanoid robot typically has over 20 or 26 degrees of freedom. So we try to reduce the degrees of freedom. Actually, the whole body motion is now reduced into the three-dimensional space. And in the three-dimensional space, for example, we have made walk motion and squat motion at the cyclic motion. And in addition to this kind of closed curve, we have integrated the vector field within this space. And we made a curve as the attractor. So the motion pattern as well as some sort of feedback control algorithms are all embedded in this three-dimensional space. So the one particular attractor, we think it's a kind of the proto-symbol of the whole body motion. Of course, in this case, we are just treating the internal coordinate of humanoid, but we believe this kind of mathematics can be extended to include the external variables like the contact force and the world coordinate, whatever. So we want to reduce the dimensionality, and we want to design the attractor in this space and treat it as a kind of proto-symbol. And of course, how we can evolve the symbols starting from this proto-symbol is the next important stuff. But this is the what we have already seen by the Professor Okada's talk. And today I'd like to start from the next things. We were also interested in how to develop a proto-symbol in another sense. As you might know, there are many hypotheses in this kind of the developmental psychology or developmental neurology. And important keyword is the mimesis or mirror neurons. And as you may know, the mirror neuron was found by Italian researchers. And they said that a particular part of neuron activated when a monkey sees his friend monkey grasp a food. And at the same time, the same neuron was activated when he himself tried to grasp the food. So the important message is that a particular neuron has bidirectional importance, particularly for percepting the other's motion and also generating his own motion. So this kind of bidirectional information processing seems to be a kind of key essence part of the emergence of intelligence. And what is also controversy is that this Italian researcher claimed that the neuron was in the linguistic part of the brain. So this is very controversy, but it's a kind of very important message. And also Martin Donald wrote a very influential book, and he emphasized the hypothesis of mimesis. And mimesis means the imitation seems to be a key part of generating the symbol and proto-symbols. So we were interested in how we can mathematically design this kind of bidirectional information processing system. And in order to solve this problem, we picked up the statistical approaches. Thanks. And we have tried to use the famous Hill-Markov model for this mathematics. And this is the Hill-Markov model. And this Hill-Markov model can be used to perceive the other's motion. and also can be used to generate his own motion. And the question is how we can develop a Hidden-Markov model and how we can use it for generating his own motion. Well, we have picked up the so-called left-to-right model, which is commonly used for the natural language processing. And it is quite simple mathematics, but the parameters, stochastic parameters, Aij and Bi, this is the key parameters. But they can be nicely computed by the standard mathematics of Hidden-Markov model. And we can generate these kind of parameters by looking at the particular behaviors. And we can capture the stochastic parameters. And we treat this as a set of parameters as a primitive symbol. And likewise, we can generate a single symbol, a proto-symbol. And of course, we have to prepare a lot of symbols or a lot of primitive symbols. But the set of symbol itself is not really interesting. We have to define the relationship between them. And to establish the relationship, we decided to define the distance between them. And again, the stochastic mathematics provide us nice tools. We use the famous Kalbach library information for that purpose. And this is the well-known the mathematics of Kalbach library information. But this is not symmetric. A to B and B to A are not equal. So we have to redefine symmetric Kalbach library information. This is a very simple idea. So this is the example. Can I show movie number 4, please? In this example, we have captured the 6 different types of motion: walk, kick, throw, stretch, squat, stoop. And this is, for example, this is a walk motion. And capturing these motions, we have computed the Hidden-Markov model parameters. So we have 6 sets of them. And computing the Kalbach library information, we can define the distance between these 6, mutual distance. And we embedded them into 3-dimensional space again. Actually, we tried to integrate them into 10-dimensional space, but actually it turned out that the 3-dimensional space was just good enough. So all 6 motions are included in this space. For example, this point showed the squat motion, and this blue square showed the walk motion. And this view graph shows the transition between them. Can I show movie number 5? Well, next movie, this is 6. Fine. So I'm trying to show my student motion, which starts from kicking motion and transit to the walk motion. So 2 motions are connected in this particular case. He is now walking, and now change to the kicking motion. And this kind of the combined behavior can be. Can I show number 6, please? So if we look at this motion in the proto-symbol space, we can see this kind of transition of the motion. So starting from kicking motion, he changed to the walking motion, then again moving back to kicking motion. So this kind of interpretation can be done in this space continuously. Well, again, can I show number 7, please? So likewise, we can use same stochastic parameters to generate the motion of the humanoid. So this kind of the perception and also perception or interpretation or the generation motion, this kind of computation is not really heavy. We can treat them almost in a real time. Well, of course, the computing the parameters takes a quite long time. Well, humanoid robot. We are also interested in challenging building nice humanoid robot. This is very competitive field, and it's hard to create something new. And can I show movie 11? Movie 11, please. Maybe this was already shown by Professor Okada, but we are trying to design the passive and active hybrid drive system. This is the one knee joint, but as you can see, this was making the passive motion, but actually actively controlled. So we can, the designed humanoid robot can change from the passive motion and also active driven motion by changing the clutch motion. This is the key idea. And finally, I'd like to show the computational stuff. Well, the part of our activity is to compute the kinematics and dynamics of the multi-body system. We have spent quite a lot of time about these things, and we have developed the so-called algorithms for structure-bearing kinematic chain, and we have implemented as the order n algorithms and also order log n algorithms. And we have also developed this kind of behavior capture studio. Actually, this room is just next to this classroom. And in this room, we have the motion capture system, which was developed in-house, and also capture the contact force from the ground, and also the system can also measure the direction of the eyeball and EMG. So these kind of human information can be captured as a sequence. So this is very important. And as a part of this project, we have developed the motion capture system by ourselves because we want to do the motion capture in real time, and we want to use this data for the control of humanoid robot in real time. So the commercial motion capture system cannot allow for us to catch the data in real time. So we have to develop. For example, can I show movie number 13.5? Well, we can attach as many markers as we like, but in this particular case, we have 40 markers. And we can capture the motion of the markers in real time. So we can do the 3D reconstruction in real time. And, well, can I show next one? Number 14. So by measuring 40 markers, we can reconstruct the motion of the skeletal system. Okay, thank you. Well, as I already explained, the efficient multi-body dynamic computation was a part of our research interest. And we have developed the algorithms for structure-bearing kinematic chain. This means the algorithm can smoothly handle any sort of the mechanisms, including open kinematic chains and closed kinematic chains, and structure-changing kinematic chains. And this computational algorithm was computed by using the efficient algorithms. And we have order n, meaning the linear complexity algorithms for this sort of mechanisms. And more recently, we have developed the parallel processing algorithm, which can handle the whole computation in order log n computational complexity. Well, since we have this sort of the measurement and computational resources, we wanted to challenge to more complex system, and by ourselves we have developed the musculoskeletal human model. This includes around 200 bones, and we have the around 321 degrees of freedom. And by using the robotics computation, we can actually compute the forward dynamics of whole body. But as you might understand, we don't know how to control the human body. So what we can do is, can I show number 18? We can just, number 18, please. Is this 18? Yeah. So this is just a natural gravity motion. I'm sorry for this scary motion, but we can just simply compute the forward dynamics of this passive motion. And if we know, and if we can develop the nice control algorithm of the muscles, we can simulate the whole human body like this. Actually, the computational time is around 2 seconds per frame. So this is quite slow at this moment. And then we can use the same dynamics computation algorithms and also the model for inverse dynamics computation. And if we apply, can I show number 19? Yeah. In this case, we can compute the ideal muscle tension. In this case, this is mathematically ideal muscle tension, but we can measuring the human body motion, we can compute the muscle tension. And I think this kind of computational resource can be used for the human-machine interface for the future, because the humanoid robot, vending machine, or any computer and machine can understand the muscle activities of a human. And of course, knowing that kind of information, I think the machine can offer something different service to the human. So I think this kind of computation can be the futuristic information for the human machine systems. Well, we have several conclusions, but our time is up. Well, thank you very much.
Thank you very much. So, actually, we are a little bit delayed, but I can take one question or two. Any questions, please?
At the beginning, you mentioned the connection from the motion, and you were talking about attractors and the relation to symbols.
That's right.
Now, could you perhaps, what we saw in the last two movies or something like that, relate to, I mean, how would you make the connection to what you basically said at the beginning?
Okay. Well, what I have talked is not really tightly connected. Our idea is that the dynamics must play an important role, generating a symbol and making a proto-symbol to the real symbolic information. Of course, as a part of the whole structure, the basic computation, basic resources to compute the continuous information, including the very direct information like the human body configuration space motion, as well as the contact force. But of course, when we see others' motion, I think we are subconsciously computing how he feels, how his muscles are activating. So I think this kind of the continuous signals, which is not very obvious, but I think being computed in our own perceptual system should be combined to generate the real symbolic or proto-symbol system.
Okay.
So, broad sense, they can be coupled.
Yeah, thank you very much.
Okay, thank you very much. Any other question? From any sides? Burning questions? I see a hand raised in Wooch. One question from Wooch. Please speak up.
I have a question. You hear me?
Yes, go ahead, please.
Do you hear me?
Yes.
Yes, I hear you. We hear you.
So I have a question. Have you tried to use artificial neural networks to control this model?
You mean the human body model?
Yes, yes.
Okay. Well, no. Answer is no. What we have focused in that particular part of project is to compute the kinematics and dynamics of whole body system. So now we are about to compute the muscle tension, not in real time, but in a quite efficient way. So of course, now what we are trying to develop is to combine this kind of the physical quantities with neural systems. At least we want to connect the, how can I say, very low-level neural systems. And of course, we have to combine this kind of information to generate the symbol system. This is a very challenging part, and I think we have to develop a lot of the sophisticated ideas to treat the cortical information processing system. But actually, we haven't done anything about the neural computation at this time, at this moment.
Okay. Maybe we should stop here. Thank you very much for the interesting talk,
Thank you very much.
Professor Nakamura. And then it's time for break. Well, what do you think? Probably we can delay 5 minutes altogether. Yeah, we at least need a 10 minutes break, right? Let's have a 10 minutes break, okay? So please come back after 10 minutes. It will be 6:30 in Japan. Okay? So see you again.
Yes, I would like to know how did they decide on designing the number of states in the heading Markov model?
Tokyo? Hello, Tokyo?
Hello? Yes, Tokyo.
Tokyo, there is a question from Jeddah. You don't see them because they don't have video.
I didn't see it. Sorry.
But
okay.
You will hear her. Okay, just
okay.
a second. Fatma, you can ask now.
You mentioned that you used hidden Markov modeling. I would like to know how did you decide on the number of states for the model you used, you implemented in the design?
Can you rephrase or repeat clearly? I cannot really hear your question. Slowly, clearly, please.
All right. I'll repeat again. You mentioned that you had implemented hidden Markov model. I would like to know how did you decide on the number of states regarding the modeling? And what was the number of states?
Okay.
And what was the number of states? 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 And what
Hi. Well, thank you for the question. So you are asking about the number of state of the hidden Markov model. Is that so?
Yes.
Okay, so there's no systematic way. So we have tested. So I think we have currently using around 20 states. But this is very flexible. Did you hear my answer? Hello?
No, unfortunately.
Oh, okay. So there is no systematic way to define the number, but at this moment we have experimentally tested, and we are using around 20 states.
Did you hear it? Currently, he uses 20 states.
Okay, I'm sorry. I can't hear clearly.
Oh,
your answer.
20 states. 20 states.
Oh, okay.
Did you get it? Okay.
All right.
I think she got it.
Sorry.
Maybe she can't see it. Difficult.
No.
She has no video, so.
Now I can.
Oh, she has no video. I'm sorry. Currently, Professor Nakamura said, currently 20, but no systematic method. Okay?
All right.
All right.
Well, I am interested
thanks
to
for
know about the details of the modeling design.
Uh-huh.
Is that possible?
Do you... Okay. So are you familiar with HMM model?
Oh, yes. That was part of my work.
Okay. Maybe you can send me email asking for references. Okay?
Okay.
Yep.
Yeah, sure.
Thanks for your question, and we have to move on to the second half, latter half of the lecture. Okay?
Thanks a lot. Thanks a lot.
Hello, everybody. Welcome back to Future Trends 2. So we are moving on to the latter half of this lecture. The last invited talk would be titled Cognitive Developmental Robotics, given by Professor Minoru Asada from Department of Mechanical Engineering for Computer-Controlled Machinery, Faculty of Engineering, Osaka University. And his field is in intelligent robots, learning, cognitive developmental robotics. And he is, again, world famous as the president of the International RoboCup Federation. So, Professor Asada, please.
Okay, thank you, Yasuo. First of all, I'd like to correct my appreciations. That was the old one. So now, currently, I'm a department of the adaptive machine systems. Yes.
I'm very sorry.
Oh, it's okay. Okay, hello, so everyone. Okay, so the title of my talk today is originally the cognitive developmental robotics, but I added three words towards the human science. Okay, so next one. Okay, the first of all, I'd like to express my appreciation to my colleague, Ko Hosoda. He had been staying with Rolf for a year, and also as my PhD students at my laboratory, and also as members of my laboratories. So as members means, no, how to back. Okay. And I mean, the other members means not simply the human robots here, but also the biological humanoids too here. Okay. Okay, and what's the humanoid science? As Professor Nakamura mentioned, there is some bilateral approach to think about ourselves. Okay, so with that, the machines we can construct, and robots, and the humanoids, and then human beings. Another way is to think about from the animals, mammalians, and primates, and then human beings here. So the way of constructing the machines and approaching the machines which are similar to us is we expect there's some new way to understand ourselves. On the other hand, also from the biological studies, maybe we can get some hints on the design of the robots. Okay, this is kind of the human science. And today's topic, I just mentioned about the the RoboCup because I'm a president. I have obligation to, as every time, to give my some brief introduction to RoboCup, what's a RoboCup, and so on. And then next, I just mentioned about the relationship to the today's talk, to the lecture so far, and human science. And mainly, I focused on the cognitive developmental robotics towards the human science, and then conclusions. So what's RoboCup? So nowadays, as everyone knows, what's RoboCup? This is a kind of attempt to foster the intelligent robotics research by providing the standard problem. Especially, I focused on some cooperation between agents, because the cooperation is very, very hard, very, very difficult problem between robots and also between the robots and the humans and so on. And so RoboCup includes various kind of research issues, not simply the cooperation, but also the design and the architecture and so on. So actually, currently we have 3 divisions. Oh, backward. Oops. No. Sorry. What's happened? I like the back. Somehow. Forward. 戻して。もっと戻して。もっと戻して。もっと戻して。Sorry. Okay. Oh. I'm sorry. I not to get used to this system. Okay. So anyway, we have the RoboCup Saga as the main event, But also we have the RoboCup Lusky as some social applications, and also the RoboCup Junior for entertainment for kids. But finally, we'd like to extend our activities for the industry applications, like Formula One. The Formula One is a competition of the cars, and we have the cars in the daily life. So suppose that maybe in 2030 or 2035, you are watching a TV program of the RoboCup competitions, and you are telling your sons or your daughter, please look at that robot. As some technology of the robot is we have also the robot in our life, something like that too. Okay, so this shows the number of teams of the RoboCup, and since 1997, the number of teams increasing. And last year we got almost 230 teams and 1,200 participants, so bigger and bigger. So this year we have the RoboCup in the Portugal, Lisbon, and also the next year the RoboCup in Osaka, Japan. Okay, so I show the 2 video clips. Okay, the first one is, could you show the first? Yes, that one. We have many kinds of rigs, and today I just showed the 2 video clips. One is from the legged rig. As you know, this is Sony Eyeballs rigs, and the teams are designed the behavior of robots and the cooperation between the robots. So, okay, and the robots try to pass the ball by head, and also pass the ball its legs or body and everything. And especially the eyeball is very cute, so kids are very interested in the behavior of the eyeballs, the movements. And actually, this shows some behavior invented by some teams, and very special. Oh, kicking. Okay, very nice. Please stop here. And show the second one. Could you show the second one? The second one is from the Humanoid League. It was held in 2002, and it was the first time to have the Humanoid League in RoboCup. And at that time, we had the Honda Ashimo teams for the demonstrations. Actually, this shows the dancing as a free performance. Okay, dancing. It's a very smooth motion, and like a human beings, like this one. Okay, it actually includes the Japanese narration, but we skip. Okay. So anyway, the Honda Ashima shows some performance of the PKs. Okay, the shooter get some position to make a shoot, and also goalie just prepare. It's like a fake. Okay, it's just only the the appearance, and then shooting. Okay, but this is kind of the demonstration of the humanoid rig. Okay. And actually, you got so many teams from the New Zealand and also from the Denmark. Okay. Very small, very cute humanoids. They tried to make a shoot, but somehow they failed. Okay. And this is the PKs of my team's Senchans against Nagara, another Japanese team. Okay. So we are using some platform designed by Fujitsu Corporations, and we modified. And this robot tried to make a shoot standing one leg and shooting. Okay, a nice shoot. And the goalie didn't prove anything. Okay, banzai, banzai. And then switching. Okay. So the robot Nagara tried to make a shoot. Okay. And then goalie jumping. Okay. So actually, this robot detects the red ball and flying, okay, jumping to save the goal. Okay, this is a flag. Please stop here. So actually, this robot injured his left shoulder, and after that, he couldn't make anything. Okay, who felt the pain? Okay, this robot didn't have any pain. I felt pain because I paid $57. Okay, but actually, I like to make the robot to feel the pain and recover from the situation and so on. So the topic here is kind of the human science to make the robot much more intelligent, much more flexible, and so on. So actually, this topic is related to the lecture 7. Already, the Rolf, gave the talk about the theory of intelligence and design principle of the autonomous agent, especially focusing on the learning and development. That's the ontogenetic perspective. So the human science is just a research vehicle where the many researchers from different disciplines gather and discussing and share some key idea of what we are something. Okay, so that's the idea. And what the cognitive development robotics is one of the idea towards the human science, because existing approaches, as you have seen, the robots, the behavior, for example, the goal is behavior is designed by the researchers. But what we are expecting is that we expect the robot much more flexible, much more, intelligent. So the structure should reflect the robot's own process of the understanding through the interaction with the environment. So the design principle of the cognitive development robotics consists of two issues. One is the design of the self-development structures inside the robot's brain. The other one is environmental design. This is mildly different from the ordinary design issues. How to set up the environment so that the robot embedded therein gradually adapt themselves to more complex tasks in more dynamic situations. As you know, in the human life, the teachers or parents or adults are very, very adaptive to the levels of the behavior of the kids or the babies and so on. So in the case of the robot, we need such kind of environment. So this indicates some example with some design issues. For the case of the embedded structures, reinforcement learning. Okay. So reinforcement learning, the neural shaders, recurrent neural network, state-of-the-art transmission, and imitations. On the other hand, as the environmental design issues, the reward functions to the reinforcement learning, the learning schedule, learning from easy mission, and so on, and the teaching, and so on. So today, I show a very simple example of the cognitive development robotics. As the content is a primary verbal imitation between agents with different articulation parameters by part-like teachings. So the infants seem to acquire the phonemes without any expert knowledge about the relationship between the sensory motor system and phonemes, and without capability to reproduce the adult sounds as they are. So how can robot do that? So we propose a kind of the constructive approach to build a robot that acquires the powers of the human caregiver. So we have the two design issues as a cognitive development robotics. What kind of mechanisms should be embedded inside robots, and what should be the behavior of the caregiver? So one is the embedded structure. The other one is design issues. Okay. So look at the human infants. The infant's speech-like cooing tend to make the mother's utter, and also the maternal imitation of infant's cooing increase the vocalization rates of a 3-month infant. So we conjecture the two issues. So that it refers to the infant's speech-like cooing, and also it helps to find a correspondence between the cooing and the phenols. So we set up the, this kind of the robot system, and human caregivers. Robot side is here, and the human is here. So robots produce some random cooing, and caregiver listen to the robot's voice and react. So how to react? So robot system is like this one. It consists of a silicon tube and 5 motors, and it make a sound. It has sound source, and through the sound silicon tube, some sound. Okay, and the caregiver listen to the robot voice and react. If the voice is like the voice the caregiver expecting, so caregivers react the same, reproduce the same voice to the microphone, and then like this one. Okay, so what kind of mechanisms should be embedded? So initially, the random articulation is here, okay, and to control the 5 motors randomly and to make some sounds. Okay, so next, the caregivers, what should be behave as caregivers? The caregiver's behavior is a part-like teaching. If the caregiver interprets the robot sound as powers, the caregiver produces a matched one. So part-like teaching is around here, and the robot listens to the caregiver's voice through the microphone. So what is the learning mechanisms? So the robot, what the robot is learning is that the robot has 2 layers. One is the auditory layers, the other one is the attention layers. So the clustering the attention parameters and the format vectors by SOM, the self-organized map algorithms, the connections are updated by the Hebbian learning. So random articulation here, and coding, and plot-like teaching input, and also through the format extractions as the audio layer, the self-organizing, and then the connection triggering. So sounding, make vocalizations, and listening, and Hebbian learning. So it shows some experiment. This shows the result of how it acquires vowels. So this shows the clustering of the articulation vectors. So you can see the kind of the clusters, Japanese vowels, A, E, U, and so on. Somehow the vowel O is not acquired due to the shape difference of the vocal tract. The human vocal tract is so complicated that the robot vocal tract is just cylinders. So there is arbitrariness in correspondence because just this shows cluster, but it is very difficult to uniquely determine the articulation itself. So we introduce some kind of criterion to uniquely determine the articulation vectors. One is the rest talk, and the other one is the rest deformation change. So we slightly change some basic Hebbian rules like this one to like this one, to considering the talk and deformation changes. Okay, and as a result, we can uniquely determine the articulation vector like this one, here and here and here. Okay, let's go the short time. So could you repeat? Yeah. Oh, so can you hear the Japanese powers? It's okay. Okay, please stop. Thanks. Okay, so listen. So the model of infant vowel acquisition process is proposed based on the mother-infant interactions, and the subjective criteria are important in imitation between difficult bodies. The future issues as motivational force of coding and learning mechanisms that work in the real world, the extension of learning mechanisms to cope with sequential vowels. The other issues we have done or we have been doing is the acquisitions of body representations for the imitations, or the development of the spatial perception, development learning for the joint attentions, or the visual imitations. So we have done and we have still been doing these issues, and I expect the cognitive development approach seems very, very promising. Okay, so still we have some mysteries. So the mysteries you should explore awareness, the consciousness, and self, or instrumentations, use of the tools, or emergence of the symbols, the emergence of communication, or emergence of language. Okay, so let's start our journey towards the human science. So see you somewhere in your journey. Thank you for your attention.
Thank you very much. Thank you very much, Sada Sensei. It was a very interesting talk. So, any questions from any sides? I have to see. Please raise your hands. Any question here? Actually, I have a question.
Sure.
In your last experiment, you introduced a term C in the Hegelian learning, which represents like how hard it is to pronounce the sound, or But since you are using an embodied system, actually, the real physical vocal tract system, I think such terms should come from the physical system itself. Your robot should try to produce the sound with a physical system and experience the difficulty itself through the physics, and then feed back to learning. I think that's the way it should be.
Yeah, that's a very good point, because actually this time only just we design prepare some criterions of the less talk or less a change of something. But actually, robot should have some kind of a sensing system. How painful of the change of the shape or something. I suppose maybe in future I'd like to apply such kind of idea to emerge such kind of a constraint. I suppose it's a real embodiment or something. Thank you for your questions. Yeah, comments.
Okay, thank you. Any other question? Please raise your hand.
That's a question in Munich.
Munich, okay. Munich, please go ahead.
Okay. I have a question which goes into the direction as the previous question. How far is it? Are the actuators which form the vowels in the artificial mechanism formed according to the natural system, the vocal tract? So equipped with sensors, will the artificial system feel the same kind of restrictions as the human vocal tract feels when it tries to form its vowels? How close is the similarity between the two vowel-producing systems? Is there mapping between how humans produce vowels in sense of actuators and the artificial system here?
Well, sorry, I missed some point of the questions. Okay, so now I got the questions. I'm not sure how close some physical system was artificial system to the natural system. But the point is that even though the hardware or system might be different, but still we can communicate with each other through the environment. That's our point of this study. So of course, as a designer, we care about some physical similarity of the artificial vocal tract to some natural system. This study itself, we don't like to care such a difference, but still we can communicate with each other. That's the point of this study. Did I answer to your questions?
What do you say, Munich? Is that okay?
The second mic.
Yes, in a part, yes. I am interested in, if you now introduce sensors, the artificial system that has a different constructive topology will feel different limitations in its restrictions in its vowel forming apparatus. So learning might be completely different from the human side. So it might lead to different dynamics, different results, and so on, different problems. But your answer was good. So I'm curious to see what happens when you introduce the sensors and go on your road. Thank you.
Thank you for your question.
Yeah, thank you. The next stage is, we introduce some sensor system because, as I showed in the, the goalie of the RoboCup video clips, we expect the robot feel some pain or something to, as a force to emit some behaviors. So next stage is I'd like to introduce the sensor system to the artificial vocal tract.
So,
thank you.
There's another question from Wooch. Please go ahead.
Hello again. I would like to ask for the very first slide you showed, when you showed us that from animals to, let's say, monkeys and then to human beings, and then on the other side from machines, robots, humanoids, and then again to human beings. So I would like to ask, what do you think about reproduction in the very, very long future? If we, let's say, have or almost a human being which is artificial, will it ever have reproduction, or will it be only created and then destroyed after its lifetime? What do you think in your vision in many, many years to come?
It's a very difficult question. So actually, every time I mention the issues too difficult is gender problem and aging. So actually, at the current rate, it does not seem that the robot reproduces itself. But in future, in a different way, the robot will be able to reproduce itself in some different ways of our own. I think so. Okay.
Thank you very much. And please greet Yoshi from me. Thank you.
Thank you. I think we are again delayed, so we have to stop here. But it was a very nice talk and discussions to summarize up the lectures so far. Thank you very much.
Thank you. Thank you very much.
So now we move up to the conclusion session. First, we want to conclude today's lectures. So I want to do it with Rolf.
Okay.
So probably, since we have our honored guest, Professor Luc Steels from VUB AI Lab and Sony CSL Paris, he's a famous top-of-the-world researcher in AI field, so happened to be here. So let's take this opportunity to have a comment from Professor Luc Steels.
Before Rolf?
Yes, why don't you make a comment now?
Okay, well, Yes, okay. Is this fine? Yeah.
Yeah.
So, first of all, I'm very excited that I could be here and, listen to all this very interesting work that's going on. And it's pretty clear that robotics is in a very creative phase of development, and I think we're going to see a lot more developments in the future. Now, I would like to come back to the statement that was made earlier, because one of the real problems that we have is still to connect, let's say, the brain, the body, and the world, and to find a kind of level. Well, it was mentioned that the word symbols, but maybe a conceptual level, I think is still an outstanding problem. And I would just like to suggest one thing, which is that perhaps we need to look more at the social dimension. That means it's not just a matter of the brain, the body, and the world. We all agree now that embodiment is a very important thing, but I would sort of like to say that perhaps one of the trends we should push for in the future is that we have multiple robots interacting with each other, because I strongly believe that symbolic layer or conceptual layer has a lot to do with the interaction between different agents or between different people. And actually what we view as a concept or a symbol is negotiated in a kind of interaction between agents. So this is one thing I would like to see as a future trend, and not just a kind of autistic agent which has no connection to other agents. This is the only comment I would like to make at this point.
Thank you very much, Luke. You pointed out one of the most important thing too important to forget, and added another step to today's lectures. Okay. So Rolf, I think you're almost bursting
No.
with comments. Please go ahead.
Okay. Well, thank you very much. Thank you also for your comment. I think it's very complementary to the sorts of things that we have been doing and maybe we have been focusing on in these lectures. I should take more time, but I will make this very short. We're running out of time here. Yasuo Kunyoshi, Britta Glatzeder, and myself will put a written summary on the webpage. So I can make my comments very short, and please, I hope that by, let's say, next week we will have the written summary on the webpage. Please do consult this summary as part of the lecture. Then I can kind of speed up these things. Originally, at the beginning of the lectures, I was mentioning two goals among several. One is, of course, an introduction to embodiment. What do we mean by it in the non-trivial sense? And also to demonstrate that things can always be seen differently. We often think it has to be that way. It must be that way. It can't be otherwise. And then to demonstrate, well, that it can be, seen very differently. Now, we have heard during these lectures, and also today, we've heard a lot of, ideas on locomotion. I think we really have the very top people here. Now, a question that we often get, from students, from journalists, well, you show running dogs, you show, well, maybe a snake. What does that have to do with intelligence? We showed this dog. So people say, well, what's the relation to intelligence? What do I do? What does walking have to do with intelligence? We had the passive dynamic walker, then we had Honda Asimo. We saw Honda Asimo today also. We saw H7 from Professor Inoue. We have been studying a lot of robotics, and we have not so much been studying chess. I mean, originally in artificial intelligence, chess was considered to be the hallmark of intelligence. And interestingly enough, as I mentioned at the beginning of these lectures, we now have computer programs that can beat almost any human being on Earth in chess. And still, that kind of work has not contributed significantly to our understanding of human intelligence. It has contributed to computer technology and search techniques, but not so much to understanding human intelligence. So I would like to sort of make somehow a connection. Also, I think that has to do with, kind of chess, sometimes considered high level, robotics, locomotion is kind of considered, low level, whatever that exactly means. And I think, and I tried to show also, maybe there's no clear distinction between high level and low level, but there's maybe more like a continuum. And I think those people who actually work on emergence, like Professor Azada, they're really interested in this particular continuum. It always starts from sensory motor things, including social interaction, of course, and then moves to so-called higher levels of intelligence. Now we saw that the non-trivial meaning of embodiment is this interplay of morphology, materials, neural control, and environment. And I think we had a very nice, very beautiful example of the snakes, where the morphology and the materials and the specific interactions are very important, and then maybe the control is not so hard. Second point about embodiment is this idea of grounding, and I think Professor Azada has been working on that. Professor Luke Steels has been working on this idea of grounding cognition, cognitive processes in sensory motor, and I'm glad I have here social interactions in my slides already, and social interactions. And then maybe one interesting comment is by Wolpert, famous neuroscientist, who hypothesizes that concerning the development of neural systems, that the evolutionary pressure came actually from a need to move and to orient in the real world. I mean, and basically, what he said is plants don't have brains. Well, they don't need brains because they don't need, that's speculation. I'm taking that from Wolpert. Well, they don't need brains because they don't need to move around and they don't need to orient in the real world. Okay, let me just briefly repeat what we had about this interplay of morphology, materials, control, and environment. We looked at this example, with the properties of the muscle tendon system, that actually, if I turn it like that, the arm will turn back into this position without neural control, and that this is kind of very good control. So basically, you get control from materials. That was the idea. Control from materials, and this was what we called the principle of ecological balance. Now, concerning the goals of artificial intelligence and the synthetic methodology, I think if you look at artificial intelligence, the topics that people are interested in have changed significantly over the last 20 years. Originally, it was computer algorithms, it was chess, it was things like that. What we've seen, for example, today is locomotion, dynamics, understanding biological systems, and I think Professor Hirose made a very nice point. Of course, we're trying to understand the biological systems, but then we're not just trying to reproduce the biological systems in an engineering system, but we're trying to find the abstract principles, and then maybe we can even engineer the systems better than natural systems, because we have possibilities that nature doesn't have. And then, of course, we also had some nice examples of practical applications. This is an overview of the design principles. I think I'm not going to repeat those. I talked about those in the past. Let me just make another comment about this issue of grounding. And you remember that what we mentioned, and that was a really important point, is that through the interaction with the real world, an organism is not just passively sitting there being flooded by sensory stimulation. But through the interaction with the real world, it generates sensory stimulation. And we also mentioned that the sensory stimulations in different sensory channels, for example, touch, vision, are correlated. So with relatively simple learning mechanisms, you can actually form cross-modal associations, and we know from developmental psychology that cross-modal associations is one of the fundamental mechanisms in concept development. And so basically what we're doing when we're physically interacting with the real world is we're generating good, what I call here good raw material for neural processing. And what's interesting about this, well, this is the principle of sensory motor coordination, right, that we discussed. What's interesting is that this generation of raw material for the brain is a physical process. It's not a computational process. But there is a direct relationship of this physical process, the computation that the brain has to do, if you want to call it computation, because the physical interaction generates the raw material. And this is a prerequisite for learning. And I think in developmental robotics, and what we've heard today from Professor Azada, I think this is an important point. We've heard earlier in the first lecture from Professor Bunyoshi who is also working on similar ideas. Last point about grounding is, I also mentioned that before, the book by Lakoff and Nunez, Where Mathematics Comes From, where they argue that even very abstract mathematical concepts are grounded in specific human embodiment, especially movement. I'm not going to repeat the arguments, but I think it's an interesting, a highly interesting hypothesis that something as abstract as numbers, or the imaginary number I, would also have its origin in embodiment. I have to speed up, but I think I'm almost done. Let me move to social interaction. I'm glad you already, basically paved the way to social interaction. We looked at Kismet, the example of Kismet. Kismet is equipped with a number of basic reflexes, and we had some videos where it awfully looks like if Kismet had very high social competence. Now you can ask, well, social competence real or as if, and of course, as always, frame of reference issue that we have discussed many times. Now, maybe you can say, well, Kismet is a robot. Well, what about people? Maybe people aren't so different. So I think it's an interesting hypothesis to pursue to see whether social interaction, socially competent behavior in people may not be emergent from simple reflexes. There is some recent work by Simon Garrett, a psychologist in England, and he just gave recently a talk at the ATR in Kyoto. Why is conversation so easy? The interactive alignment, the kind of dialogue processing. So we're all, we may have difficulties giving a talk. Students confirm that when they have to give a talk, or even professors. But we all can very easily talk. Now, why is that? That's because we kind of align to what the other, that's called the alignment time. We align to what the other is doing. So maybe very simple mechanisms make conversation easy. There's also a recent paper, well, not so recent, a few years, by John Bark and Tanya Chartrand in New York, titled The Unbearable Automaticity of Being. What they're arguing is that a lot more is purely automatic, reflex-like driven, and is of course, to me, an illustration of this principle of cheap design that we had, for locomotion, for sensor morphology, and things like that. But this time applied to so-called higher-level processes. So maybe, the difference isn't as big as we would think. Okay, I'm almost done. I want to save some time for Angelica. So I think I only have 2 slides left. Perhaps the hypothesis that so-called high-level intelligent behavior, such as conversation, social interaction in general, might be emergent from simple reflexes rather than complex thought processes, or to use the quote from David McFarland from Oxford University, rational behavior that looks very goal-directed or rational, does not need to result from rational thought. Hence, can display rational behavior against, you have the frame of reference issue. No, I cannot advance the slide anymore. Well, there's a problem with the technology there. Maybe we can go on the PowerPoint control. We have a problem with the technology. Okay. Let's see, the next to last. Well, sorry. I can't, again, I had the same problem as Professor Nakamura. I can't really go back. Well, I think, some people mention challenges. Professor Asada mentioned challenges. Here are a few, abstract thinking, natural language. We're not saying that we have the solutions or we have all the answers yet, but I think we have an approach. And bottom-up synthetic methodology, design principles, and of course this issue. Now, I think we should probably switch, for reasons of time, to Munich. And I would like to ask Angelika Beck to present the slides, and we have to get the other presentation. Okay, let me give the where is the where's the live logo without? This one? Oh, you changed the name. Well.
Hello?
Actually, well.
Die anderen bitte.
Huh? Okay, we have to go to
Die Slide.
This is the wrong presentation. Sorry.
Good morning, a lecture
It's the wrong
community.
presentation. It's not here anymore. Live logo without photos. Not this one. No, because no, it's another one. Can you go to the folder? Can you go to the folder? It's without. Go to the folder. Just the folder. Yeah. Without photo, because we changed the. You have a lecture 10 folder, right? That was the one. Yeah. We'll go with that. This one. Yeah. This one. Okay. That's it. Sorry for the delay. Right. Here we go. Okay, Angelika, you want to comment?
Today I would like to give you a preview of the AI lecture from Tokyo's Art and Science project. Professor Pfeifer and Dr. Glatzeder have been asking me, being an artist, whether I could develop a logo for the AI lectures from Tokyo as a piece of art and science. I did what they said. If you have visited the website of the AI lectures during the last few months, you might have noticed a white circle on the bottom right corner of the page. And if you clicked on it, it popped up in a larger scale. You see it here on the right-hand side, with a few words of explanation. This picture stands for the AI Lectures logo until its realization, that will be hopefully completed tomorrow. We would, of course, have liked to show it to you today, but there has been a delay in transportation. Insofar, please visit the website tomorrow. This logo will be, of course, the logo for the next year's AI lectures. I would like to say a few words about the artistic concept. With the growing and flexible global teaching community in mind, as well as the differing time zones of the project partners, I wanted to create a point of reference that stands for the imaginary center of the community. This idea takes its patterns from the Zero Meridian, which runs through Greenwich by London, and that got internationally acknowledged in 1884. Besides the very practical aspect of this agreement, the fascinating point for me is that the Zero Meridian almost physically locates an idea. The global teaching community, whose interests and goals are to achieve more and more knowledge about the basic topics that humans have possibly always been interested in, like evolution, nature, or intelligence, for example, should likewise refer to a point of reference and build a network of science. The Earth's poles are, of course, especially qualified as geographical locations. In the first place, the two poles have a fixed position in our consciousness. In the second place, and this, I believe, is equally important, they are out of reach for almost all of us. Throughout history, reaching the pole was one of the major scientific endeavors. Researchers of different nationalities headed for the same goal. The poles became the symbols of scientific ambition itself. The Live logo shows a permanent 360-degree view of the globe from the South Pole. We are very happy that we are allowed to install a video camera at the German Antarctic Research Station, which you see very grey here now. And this station is called Georg von Neumayer. I would like to thank all those who helped realizing the Art and Science project. Dr. Paulens and Dr. Pfeifenberger, Alfred Wegener Institute, Bremerhaven, the technical crew at the German Antarctic Research Station, Georg von Neumayer, Hartmut Babka Basis System, Andrea Witt Max Vision, Dr. Laut Jen Optik, Hanspeter Kunz and Nathan Leppard, AI Lab Zurich, Walter Heimanik Adon, Wien. And I would especially like to thank Dr. Glatzeder, the AI Lectures project manager, because without her enthusiasm and power and persuasive power in getting our partners interested in the project, we would possibly not have been able to realize the Live logo. Thank you very much for your attention.
Okay, well, thank you very much, Angelika, for fascinating ideas on these lectures. I would just like to point out this webpage, and this is actually the airplane which is responsible. Oops, what happened? Yeah, this is the airplane on which the camera was actually brought to the South Pole. So unfortunately, with a small delay of about 1 day, and so we couldn't show it today. But this is the airplane, and you can view the web page here. Okay, so let me go back. I think to the very final slides here. So we will provide a summary statement because today was obviously very short and we couldn't go into any details. So I hope that next week we will have this summary statement. And so thank you all for participating, for joining the AI lectures from Tokyo, and stay tuned for future developments. Thank you very much. So maybe you want to make a final statement, Yasuo?
Thank you, Professor Pfeifer. It was a very nice conclusions. And so I take the honor to say a few words. Well, before starting up the lecture, I think everybody involved in this lecture didn't know what to do in the beginning, but at the end, our team's very efficiently working, and everybody's cooperating, and so that was the power that made this global endeavor possible. And after this lecture, I think we can move forward into the future, enhance our global cooperation. So I want to sort of dream with all of you for the forthcoming enhanced version of global virtual lectures. Britta, do you want to say a few comments? Okay. So maybe it's time to declare the end of this AI lectures from Tokyo. All the participating sites, thank you very much for all the cooperations. Thanks for all the team members in all the sites. Here we declare the end of this AI lectures. Thank you very much. See you again sometime in the future. Thank you.